Hello everyone, and welcome to the proof of concept presentation for the Oasis instrument, being developed as part of the 2020 NASA Big Idea Challenge by the Penn State Student Space Programs Laboratory, or SSPL for short. This talk will first introduce the Oasis system in general, so that the rest of the talk can be more easily comprehended. The remainder of the talk will then discuss methods of system verification, which for the purpose of this talk include preliminary LIBS testing, thermal simulation, and integrated testing, all of which my colleagues will discuss in further detail. But first, an introduction. My name is Ralph Cordiano. I'm the lab manager for SSPL and also have acted as the project manager and systems engineer for Oasis over the last year. To start, Oasis is a rover-mounted spectroscopy instrument being designed to operate within PSRs, or regions of the moon that never see sunlight. Previous NASA missions have indicated immense amounts of water in these regions, and thus, as part of the 2020 NASA Big Idea Challenge, Oasis is being designed to survey these regions for water. To do this, Oasis will use laser-induced breakdown spectroscopy, or LIBS. With LIBS, a laser ablates a sample, in this application lunar regolith, and a plasma is generated at the point of contact between the laser and this sample. This plasma will then generate emissions of light at certain wavelengths, which we will discuss in the subsequent slides. Before we get to that, just a quick note. This is a general diagram of how LIBS works in many traditional applications. However, it's important to note that Oasis does not actually use a mirror, which is depicted in this diagram. But moving on, the wavelengths of these emissions then generate a spectrum, which, when recorded by the spectrometer, can be used to determine relative chemical composition of the original sample. These are some spectra used throughout traditional LIBS applications and give a rough idea of the data that LIBS instruments return. In particular, Oasis will operate within the 250 to 800 nanometer range, which will detect many elements, including silicon, titanium, and iron. However, it is important to note that while it can collect the wavelengths of many elements shown on this table on the left, the primary goal of Oasis is to detect water, and the primary elements relevant to that are oxygen, hydrogen, and hydroxide, or OH. To maintain operable temperatures within the payload, Oasis uses a combination of active and passive heating systems, which we will now discuss. Our active heating system consists of Kapton etched foil heating elements, shown on the left here, run by a microcontroller purely dedicated to operating the thermal system. This microcontroller will then power these heaters on a pulse width modulated signal, and the heaters will heat our payload components through conduction. A general diagram describing the operation of the thermal logic controller, as we refer to the microcontroller, is shown on the right. The Oasis aluminum housing exterior will be polished, allowing it to radiate heat at a rate such that the active heating system can put enough heat into the payload components to maintain operable conditions. This is the general premise of the Oasis payload environmental control systems. Heat is put into the payload components by etched foil heating elements and radiated out of the exterior by the polished exterior. Doing this will allow the payload components to maintain operable temperature ranges throughout our mission. Last but not least, a general diagram of the layout of Oasis. Starting from the northernmost wall of the Oasis payload, we have the spectrometer, and then to the right in blue, the laser driver. The laser driver generates the power that goes through the laser head and comes out the other end to be focused by the optics shown in front, which we refer to as the beam expander. On the left, we have our blue PCB with our power system and the BeagleBone Black industrial flight computer mounted to that system. Last but not least, we have the spectrometer telescope optics that are connected straight to the spectrometer via fiber optic cable. One quick note. The spectrometer fiber optic cable goes to the telescope which is angled in the payload wall. The reason it's angled is to have a more direct visual contact with the point of ablation, allowing for more accurate data readings. Now, Norman Yu will discuss our preliminary LIBS testing.
Hello, my name is Norman Yu, and I'm the electronics lead for this mission. I'll be describing the preliminary LIBS testing section of this proof of concepts presentation. Despite COVID restrictions, we are very fortunate to be able to test our laser-induced breakdown spectroscopy system at the Naval Research Laboratory facility. This test successfully verified the spectrometer laser interface software for the flight computer, a BeagleBone Industrial, as we can see here. This flight computer can successfully command and receive data from the spectrometer and the laser, and this is the laser command box, and this is the laser diode. The laser beam expander and the spectrometer telescope were also tested in this test. Finally, our thermal team also gained valuable insight on the heat output of the laser diode when it fires. Ultimately, video footage taken from this test confirmed that the laser successfully ablated simulant lunar regolith, as we can see in this picture. We can see this in this video as well. While the previous video shows that the test conducted in a lit environment, the test is typically conducted inside a black box, so the spectrometer is sampling in an environment similar to the permanently shaded region of the moon. Still, the sample data, as we can see here, indicated significant and overwhelming noise in the spectrometer's reading. Based on the data, many potential solutions have been proposed and implemented to solve this issue. The first possibility is that the spectrometer's optical system is misaligned. Data from sampling known light sources have shown that our system is quite sensitive to misalignments. This issue would be solved when we successfully integrate our spectrometer into our payload housing. Data from our tests have also shown significant jitter or inconsistency in timing between spectrometer sample and laser fire. The inconsistency necessitated a longer sampling duration in this test. In order to lower the jitter and allow for shorter duration sample in the future, which would reduce the spectrometer noise significantly, an external trigger which can simultaneously command the laser to fire and the spectrometer sample should be used. With this method, the laser has a delay option to ensure predictable latency between laser fire and spectrometer sample with low jitter. Our team has already begun breadboard development of this external trigger, and we're confident that this issue can be solved with minimal design changes. Furthermore, data from this test indicated that microsecond spectrometer sample might be required. Consequently, spectrometer models with shorter integration time should be evaluated. The manufacturer of our current spectrometer, Ocean Insight, have spectrometers with lower integration time, similar dimensions, and identical interfaces, allowing them to be swapped in without significant changes to the design of Oasis. Finally, the data indicated that the spectrometer's charged coupled device generates initial static electric noise upon sampling, which is too great for the laser ablation to overcome. One possible solution is to sample multiple times and average out this initial static noise. Fortunately, thermal data collected from this test indicated that the laser could fire in quick succession without overheating. In other words, we can fire the laser and sample in rapid succession. Provided an adequate heat sink, this issue should be even less of a concern in a cryogenic environment. In summary, preliminary LIBS testing has verified the laser's ability to ablate, the software's ability to control the instrument, and the thermal system's ability to manage the heat output of the laser firing. Furthermore, it has informed several design solutions surrounding noisy data. This sets a strong foundation for the continued development of the Oasis LIBS system. Up next is Sam, a co-lead of the thermal subsystem, to discuss the thermal simulations.
Hi, my name is Sam Larner, and I am a thermal subsystem co-lead for the Oasis project. Today I am here to talk about the thermal simulations used to verify the thermal control system. A thermal model of the payload was made in COMSOL multiphysics to simulate the components in a PSR environment. All of the components were modeled with their approximate dimensions and physical properties through COMSOL's built-in geometry tool. An environmental temperature of 20 Kelvin was used for this model to account for a worst-case scenario. The power consumption of each component was modeled as a constant heat output on that boundary. Thin boxes were used to model the heaters that are attached to their respective components and supplied a certain amount of heat output. Lastly, the outer surface of the housing was modeled with a boundary condition that allowed a specific emissivity to be inputted to test slight variations in the emissivity of polishing the aluminum. The target emissivity of the outer surface needed to be determined through the simulation. It was known in advance that the total heat output could not exceed 3.3 watts. The operational temperature range of each component and the center temperature of that range was also known. The emissivity and heater power output were both varied until the error between the simulated temperature of each component was within 1% of the center temperature of the operational temperature range. Many different emissivity and heater power output combinations resulted in the correct temperatures for the components. The target emissivity was chosen to be set at 0.0425 because at this emissivity, the heater power output was close to the middle of the 0 to 3.3 watt acceptable overall heater power range. It is known that the emissivity from polished aluminum is between 0.04 and 0.051. The target emissivity for the payload of 0.0425 is within this range, but it is unlikely that the polishing the aluminum will produce this exact value. As seen from this graph, the heater power output needed to maintain component temperatures is under the 3.3 watt max from an emissivity of 0.0425 up to about 0.06. This means that even with some variation in the emissivity of the polished aluminum, the heaters can still maintain the temperature of the components. If the emissivity goes lower than 0.0425, the aluminum can be roughened slightly to provide an emissivity within the range of 0.0425 to 0.06. Now here's Drew McConnell to talk about the integrated testing.
My name is Drew McConnell, and I'm the project scientist for Oasis, and I will be talking about the integrated testing. This integrated test will occur in a cryogenic thermal vacuum chamber in which ablation can take place, such as Vacuum Facility 13 at NASA Glenn. An integrated test will be used to verify that both the LIBS and the thermal control systems can operate simultaneously in a simulated lunar environment. Once the payload is in the chamber, the pressure will be dropped. Then the temperature in the payload will be incrementally decreased to ensure that the components inside the system are not damaged. This test will verify that the heaters inside the housing and the coating on the exterior of the housing are sufficient to maintain the desired temperature inside the payload. Furthermore, this test will verify that the PI coefficients have been correctly calculated, allowing for the thermal control logic controller to regulate the temperature of the instruments. Upon reaching this minimum temperature, LIBS will be performed on a lunar regolith simulant. While a preliminary LIBS test did take place, this test was only in laboratory conditions rather than in a simulated lunar environment. The low pressure that's present in a lunar environment causes the laser-induced plasma to both expand faster and have a cooler temperature, resulting in the intensity recorded by the spectrometer to be less for lower pressures. This test will ensure that Oasis can perform LIBS in these lunar conditions. During testing, data will be transmitted to laboratory computers in real time to ensure that instruments inside the payload are within their required operating temperatures. This will verify that the communication protocol is functioning properly through the RS-422 communication line.
Thank you for watching this proof of concept presentation. In this talk, we discussed the Oasis system in general and the system verification methods used, including the preliminary LIBS testing, thermal simulations, and integrated testing. We hope you found this talk informative and that you are now as excited about the future of the Oasis instrument as we here at SSPLR. Thank you for your time.